Now we have a situation where our motion is downward, our resistance is proportional to the square of the velocity. So our motion's downwards, and we know that gravity is acting downwards, but our resistance is proportional to the square of the velocity. So that's what we're looking at. So first we want to look at getting our terminal velocity, and we get this expression. So we know that mass times acceleration equals mass times gravity minus mass times k times v squared. So acceleration is minus g minus kv squared. And we know when terminal velocity occurs that a is equal to 0. So we sub that in, manipulate our algebra, and we get v is equal to g on k all to the power of a half, or the square root of that. There we go. So that's keep in mind the idea that when we got terminal velocity, well, what does it mean? It means that the velocity can't get any faster, so it means there's no more velocity. It's reached its maximum velocity, and that occurs when acceleration is 0. So this time we've got a velocity of the particle. We want to find the velocity of the particle at time t. So we got dv to t. We're going to start with that. So dt to v would be written as 1 over g minus kv squared. Integrate both sides. So that gives us, going to give us t. And we need to get this to the point where we've got the 1 over g on k minus v squared. Now, when we look at that, that can be broken up into two expressions there. So it's a difference of two squares. So we get those two expressions now, which means that when we do that, that can become v, because it's square root of g on k, square root of g on k. So it's where the v's come from. But when we're looking at this, to break it up to that one, we'll need to use partial fractions. So you need to solve some partial fractions with that one and put it in terms of v, but they both work out as 1. So I haven't done the partial fractions here, but that's how we get down to that expression. And well, they come out to 1. Well, technically they come to a half of square root of k on g for both of them. So that's 1 on v. So that's where that's coming from. So that's, if you do the partial fractions, that's what you would get, which we can factorize both those out. So that's where we're going to get the 1 on k times the half. Square root of k on g becomes the 1 on 2kv. That will integrate to give us natural log of v plus v minus natural log of v minus v plus v. So v minus, that should be a minus v, plus our constant of integration. So our expression there plus our, to get our constant. And we know when t is equal to 0, velocity is equal to 0, so our constant will work out as 0. So that's nice, because we don't get very nice. We get natural log of v on v, so which is natural log of 1, so that's 0. So that's where it comes from. And we get 1 over the 2kv, natural log of v plus v over v minus v. And then we want the velocity by itself. So we start to manipulate and multiply through, use our definition of logarithm. Again, multiply to get rid of our denominator. We collect our terms in the little v, so we take that across. A little v there would be equal to either the 2kvt plus 1, and then we've got to collect our other terms across here for the capital V, and then we start to divide, and then we were able to get the expression that we need. So have a look at that algebraic manipulation to get from that point to that point, whether we're multiplying through, using the definition of logarithm, collecting terms and factorizing and dividing. So be really careful with that. This time we want the position of the particle x in terms of v, and that's given to us by that expression. And we hence want to find the distance y. Requires a velocity v given that expression. So what does that mean? Well, we want to get x in terms of v. So we start with v to v dx, and again we get the division by v, and then we take our reciprocals, And again, this one works out nicely. It's sometimes they work out nicely, sometimes not so much with the integration. So x there is equal to minus 1 on 2k. Because really what we need is a minus 2kv there. So we're minus 1 on 2k, natural log of g minus kv squared, plus our constant. And when v is equal to 0, x is equal to 0. So we get 1 on 2k times natural log of g. And our expression for x comes out to be that. Once we put our constant together with that expression. So that's not too bad. The second part there, if we substitute x is equal to y, we get that expression. So at some point y. And then we start to manipulate y to get, so y in the v in terms of y. So we've multiplied through by 2k, taken the definition of a logarithm, and then we start to play around with this. We want v by itself, so we'll take the reciprocal of both sides, cancel the g, we get the kv on v squared, we get that by itself, take the other one across, and then divide by g on k and take the square root. And we saw that minus square root of g on k was equal to v, so that's where we were able to get our expression. Again, the algebra, be careful with it. If the projectile now is projected upwards in the same medium, its initial speed of v0 and returns to the point of ejection with speed w, show that you get that. So again, we've gone to, as we said before, if we start with motion upwards and then downwards, we start with our new point of origin. So we're going v to v dx is minus g minus kv squared, because our resistance is, our particle's moving upwards this time, so it's minus g. So again, we manipulate it as we've done before. We get the minus 1 on 2k natural log of g plus kv squared. And when x is equal to 0, our velocity is v0, so our constant would be given to us by that expression. It's the opposite of that. So we can get x is equal to 1 on 2k natural log of g plus kv squared, v0 k squared on g plus kv squared. When we know our greatest height is at when v is equal to 0, so we get our value for h there. So we also know the particle attains the speed of w when x is equal to h from part C. So we get h is 1 on 2k natural log of g minus kw squared. So get those two expressions equated. So we get a g squared there, and multiplying these two out, we get g squared kg w squared kg v0 squared k squared v squared 0 squared w squared. That's a lot of squaring. We start to cancel our g squareds. At least something's nice. So, and then start to get this part across different sides. So we've taken these two across one side, so we're all now positive values, and we start to do some divide some expressions. So we divide by the k, divide by the g's, and we get the 1 on w squared, divide by w squared as well, divide by v0 all squared. Things start to cancel out, so be careful when you do all that division. We get k on g plus 1 on v0 squared plus 1 on w squared when we've divided everything through there. And k on g is the same as 1 on v squared. So that's where we get our expression 1 on v squared plus 1 on v0 squared equals 1 on w squared. That's a bit of work. So be careful as you go through. It's really taking care with all that algebra that we make sure we don't make simple errors that stop us from getting through to the final result.